Here let's examine the solutions for the Schrodinger equation for a 3D rigid rotator, which we talked about earlier. It turns out that the solution to that equation, we'll go back up here, here it is, the Schrodinger equation, where the Hamiltonian is expressed in terms of the spherical coordinates theta and phi. Turns out that that solution is, well, it's been known for a couple hundred years, called spherical harmonics, and that's given the symbol usually Y sub L, M sub L. All right, so spherical harmonics. If you go through the solution, what you do is you take this wave function, which is a function of these two spherical coordinates, and you then separate them, do separation of variables like we did for the multi-dimensional particle in a box. So here is a function that depends only upon the theta angle, the spherical coordinates, and here's a function that depends only on the phi angle. So you separate coordinates, and you can do this if there's no correlation between these two variables theta and phi, which there isn't. Okay, so when you separate the variables, you can separately solve for the phi dependence, and this you may recognize is the solution for particle on a string. And here's the quantum number m, 0, plus minus 1, plus minus 2, and so on. So that doesn't change. However, the dependence on theta does change. And let's just refresh our memories what these coordinates are. Actually, let me draw it a little differently here. Let's draw it this way, a little clearer if we draw it this way. This will be the x direction, this will be the y, and this will be the z direction. And now we have a vector of constant length which points out into space. If we project this vector down to this axis here and draw this projected vector, we have an x and a y component, and we have a z component. Theta, recall, is this angle of the vector with the z-axis. That corresponds to latitude, if this is the North Pole. And this angle phi goes around here. That will correspond to longitude, again, if this sphere is oriented, so this is the North Pole. So we separate out the dependence of the wave function on this angle and on this angle, and we find that the dependence on that this angle here relative to the North Pole, which gives you the latitude, is called the associated Legendre polynomial. So let's just go to the associated Legendre. Let's see, here we go. Not there. Associated Legendre polynomial. Legendre was a mathematician in the 1800s. So this is the differential equation that you get, and actually this is very similar to the one you would get for trying to solve the Hamiltonian, or the Schrodinger equation with that Hamiltonian. And the associated Legendre polynomials are expressed as the derivative of Legendre polynomials. So we have to go back here. Here's Legendre polynomials, and there's a quantum number associated with them. In this case it's L, but in the previous slide we had, or in this case it's N, previous slide we had L. So there it is, it's just polynomials. And then to get the associated Legendre polynomials, which are the solution to the Schrodinger equation, you take various derivatives of them. All right, so that's what that is. And what is interesting about this is that each one of these functions has associated with it a quantum number. The phi quantum number is n sub L, and the theta quantum number is L. But this theta depends not only on its own quantum number L, but on the quantum number m sub L of this function here. So you have two quantum numbers associated with the that angle that gives you the latitude on the sphere. Well, that's interesting. So if you solve these, solve the Schrodinger equation and express theta and phi in terms of the angles theta and phi, you get what is known as spherical harmonics. Let's take a look at the Wikipedia articles on spherical harmonics. Here it is. There was the coordinate transformation we made earlier. Here are the spherical coordinates, spherical. And again, what you have is two quantum numbers, L and M sub L. And if we look at this should look very familiar. So if L is equal, M sub L can go from 0 all the way up to plus or minus L. So if L is 0, M sub L can only be 0. If L is 1, M sub L would be 0 or plus or minus 1. This should look very familiar to you. These are the quantum numbers that you talk about when you talk about atoms in the periodic table, or when you talk about the hydrogen atom. We remember that from introductory chemistry. So this is L and M sub L. If L is equal to 2, you can have 0, plus or minus 1, plus or minus 2. So you can have 5 values of M sub L if L equal 2. Oh, look at that. S, 1 value S. L equal 1, you can have 3 values, px, py, pz. L equal 2, you can have 5 values of M sub L. That's the d, xc, dy, the 5 d orbitals there. So that's what that is. All right, so if we go back here, here's the actual functions for L equal 1. That corresponds to like the s orbitals. There it is. Look that there's no dependence on theta or phi. In fact, this just corresponds to a sphere. So the wave function is independent of direction when L is equal to 0. For L equal 1, we can have 3 values of M sub L. And here they are. This is L equal 1, M sub L equal minus 1, 0, and plus 1. And this is just the solutions to the Schrodinger equation for particle on a sphere. And again, it's a function of 2 variables, phi and theta. That's interesting. And note that this has imaginary components in it. And we'll talk about the real, how you get that real in just a minute. And then with L equal 2, okay, we have these 5. M sub L equal minus 2, minus 1, 0, plus 1, and plus 2. These are the actual functions, and they depend upon theta and phi. So let's actually plot these functions. And here they are plotted. This is the L equal 1, M sub L, L equals 0, M sub L equals 0. It's just a sphere, just as we thought. There's no dependence of the angle. Here, this row here is for L equal 1, M sub L equal minus 1, 0, and plus 1. So he has the 3, and these look like the 3 p orbitals. Oh, that's interesting. And here is the L equal 2, 1, 2, 3, 4, 5 values of M sub L, and that's what they look like. So what you're doing here, what kind of plot is this? Well, you're plotting the distance from the origin to the surface of the sphere is the value of the wave function as a function of these 2 angles. So for instance, the distance from the center of this sphere out here, as the angle varies, for the L equals 0 is just a constant. Remember, L equals 0 is just a constant. 1/2 of square root of 1 over pi. So you get that. On the other hand, if you vary theta and phi here, the value of the wave function will vary. So here's L equal 1. So depending upon what values you have of phi and theta, you have a different value of y sub L. And so what this is plotting from the origin, if that value is 0, it's 0. Out here, it's some value here. So this is the value of the wave function plotted from the origin as a function of the theta and phi. Okay, and then we can go down here. This is the L equals 0, 1, 2, L equals 3. You have 1, 2, 3, 4, 5, 6, 7 possible values there. So, and these look like orbitals. That's interesting. So the spherical harmonics are the solution to the Schrodinger equation when the Hamiltonian is expressed in spherical coordinates. Now let's look at the energy. The energy here depends upon only one quantum number. That's the L quantum number. L plus 1, h bar squared over 2I. And remember I, well, let's just go here and write it on the here. So energy is equal to L plus 1, h bar squared over 2I. I is the mass of the particle times the radius of the sphere. Again, this is a particle on a sphere. This is the radius of the sphere. Okay. So this depends only on L. Does not depend on m sub L. So if we look at those spherical harmonics, all the ones L constant, this has the same energy as that, has the same energy as that. So for L equals 0, there's no degeneracy, but for L equal 1, it's threefold degenerate because there are three values of m sub L that all have the same energy. Remember, m sub L can go from minus L to plus L in integer steps. So if L is equal to 1, m sub L can go from minus 1 through 0 and plus 1. All of those have the same energy, and so on. All right, so I think we've covered the major points of the solution of the harmonic oscillator, of the, what am I saying, of the 3D rigid rotator. Let's go for one additional item here. These are the solutions to the Schrodinger equation when you express the Hamiltonian and the wave function in spherical coordinates. And these are the spherical harmonics. So these are spherical harmonics. So you can show that if you integrate over all space, and we have to have a sine theta d theta because we transformed from dx and dy and dz into theta, r theta and phi. If we can show that the wave functions you obtain, these spherical harmonics, are orthonormal, namely if you integrate from, and now we have two variables, we have theta and phi, so we have to integrate over both variables, over all space of those variables, then we'll get 1 if L and L prime and m sub L and m sub L prime are equal. In other words, if they're the same quantum numbers, same set of quantum numbers. Now we have to worry about two quantum numbers, L and m sub L. If L and m sub L were the same, we integrate that, we get 1. Otherwise, if L is not equal to L prime and m sub L is not equal to m sub L prime, one or both cases occur, then the overlap will be 0, and that's the requirement for orthogonality. So they're normal and orthogonal. Also, let's look at the limits of integration here. Theta, d theta, is integrated from 0 to pi, whereas phi is integrated from 0 to 2 pi. Why do the two limits of integration differ? Why don't you go from 0 to 2 pi for both of those? Well, let's look here. Let's see. So what if you have going from 0 to 2 pi, you circle all the way around here. So let's start with the angle to be 0. As this angle increases, you're circling, circling, circling. This angle goes down all the way to the South Pole. So for as phi circled all the way around for each angle of theta, you describe the entire sphere only by going only from 0 to pi for theta. If you went from 0 to 2 pi for theta, then you describe two spheres, one sphere going down and one sphere going up. So if phi goes all the way around, theta only has to go from 0 to pi. So that's why to integrate over all space, the theta only has to go to pi, whereas the phi goes all the way around the z-axis. Okay, so I think with that point, I think we're done discussing the solutions to the 3D rigid rotator.